Yeah, so we're halfway through on week 4, and today we have Dr. Mohammad Reza Mahibian to tell us about the deep learning framework Pytorch, especially the training and evaluation process. So we're finally getting into some flavors of deep learning models and their utilizations. So I see people are trickling in. I'm going to just go ahead and start share our screen, share my screen here. Great. Happy Sunday, everyone. As I said, today we'll talk is the workshop that's going to touch on model training, evaluation, and PyTorch. If you don't know which land you're on, please go ahead and click on that link. Our virtual event is based in Montreal, Quebec, which is the traditional territory of Kanakahaga, and is on land that has long served as a site of meeting and exchange among Indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse Indigenous peoples whose presence marks the territory on which peoples of the world now gather, and we encourage you to learn and discuss about the history of the land on which you reside on. And Victor has been sending you emails through this info@McMedHacks.com email. Check your spam folder if you don't get them, and please do whitelist both medhacks2021@gmail.com as well as info@McMedHacks.com. You can feel free to send questions to either of the emails. Please treat your fellow participants with respect and remain muted during the presentation to not distract the speakers. And our Discord channel will be active. As I mentioned before, we're in the middle of the summer school in week 4. And this week we'll have 2 workshops. Yesterday we had a seminar session with the wonderful Dr. Marian Asnar, as well as Dr. Oduna. And then we are having a workshop today as well as one on Wednesday. So Dr. Mahibian is also going to talk about that workshop, lead that workshop this coming Wednesday as well. Just a reminder. And we have one mentor this week, Ni. You have been with her before, so welcome, Ni. Thank you again for helping us and being a part of the program, being our mentor. But we have not set up a time for this week yet, so for the tutorial. So we'll communicate that in the email. And again. Yes, I said the same thing yesterday. I'll set up the bot, and that will actually be done and be demoed on Wednesday. So we have a bot where you can check your attendance and so on. So 70% of the workshop attendance and 50% of the seminar attendance will be counted. Yeah, so great. And Ni, are you here? You guys have met Ni before. She's one of our mentors. So if you want to say hi, please go ahead and say hi to everyone. And reintroduce yourself if you want to.
Yes, hi, I'm Ni. I graduated from McGill in computer science and biology. I will be mentoring this week. Yep, that's it.
Great. Short and sweet. Awesome. So today, I would like to introduce our instructor, Dr. Mohammad Reza Mahibian, and he has received his bachelor's and master's degree in biomedical engineering from the University of Isfahan. He achieved a PhD degree of electrical and computer engineering from University of Saskatchewan in 2021. He worked multiple years as a machine learning engineer in industry in the field of natural language processing, NLP, and computer vision. He has co-authored 3 book chapters and over 35 peer-reviewed journals and international conference papers in the domain of health informatics, pattern recognition, medical imaging, signal processing, and machine learning. So it's really a pleasure to have you to be our instructor today, Mohammad. Please go ahead and start your workshop.
Thank you so much for introduction, and I'm happy to be here. Thank you for invitation, and thank you all for joining this conference. I will try to walk through the model training and evaluation. I'm not master of all, so I will try to go through this course line by line, and maybe sometimes we need to search. And let's go. The first of all, I think you have heard about what is Pytorch. So the Pytorch is an open source Python library for deep learning, and it is developed and maintained by Facebook. And the project started in 2016 and quickly became popular framework among developers and researchers. That recently, about more than 70% of the researchers are using Torch. So the Torch is an open source project for deep learning written in C. So we should not make problem when we say what is Torch or Pytorch. So Torch is the base of the Pytorch that currently we have, and Torch is written in C and usually using Lua interfaces. And after that, there are some precursor projects to develop Pytorch, and Torch is not actively developed now. But as you know from the previous courses, so we want to use the Pytorch. I know that you have passed like the courses related to how backpropagation happen in the Torch, and also how we define variables and tensors in Torch. So in this course, I'm trying to more talk about how I want to train and evaluate the model. And I will go through the documentation of the Torch each time that we need it. So the first thing we need to is install Torch. And for installing Torch, let me, okay, can you see my screen? Yeah. So I just want to show you that if you want to install Torch, so we can, for example, type in the Google how to install Torch. So we have Torch installed. If we're in the first page, so we can install it in different way. Like if you have, if you want to use it by PEEP or Conda, or if you want to use GPU or CPU, so we can have different option. So for example, if I want to install it using CPU and the stable version in my Windows, I can use this command using Conda or using this command using PEEP. So for my case, I don't need Torch Vision. I don't need Torch IDEO. I just need Torch because these are different libraries used from Torch, but they have some tools that are specifically designed for like vision, computer vision, and also the audio. So for this case, I just install PEEP install Torch, and if I run that, so it's because I already run that, it said that requirement already satisfied. And if you are running it for the first time, I think the Colab maybe they have already installed it, so you don't need to worry about it. The next thing that we need to do is be sure that the Torch version is what version we have installed, and have we installed the Torch version with the Coda library or not. So the next part is to understand this. And if we see like this 1.11 plus CU 11.3, it means that we have installed Torch with this version, and that support the Coda library 11.3. So it means that if we are, for example, using the Jupyter Lab, so we can go to the Jupyter Notebook, we can go to the edit, and in the netbook setting, we can select that we want to use GPU. So in that case, if we have installed the Coda version and we select the GPU, so we can run the notebook using the GPU. So I think I'm just explaining something that is explained before, but just to starting my conversation about how I want to define a data set and others and going to the documentation, I think it's necessary to know which library we have installed. So the first thing for training a neural network is data. So we have to prepare our data, and that data can be images, that can be structured data, can be CSV files, anything. And Pytorch designed a class called datasets, that these datasets can be used for creating our a generator for data. So if you already know that what is generator is, that I think Farhad in one of the courses support that how generator is works. But basically generator is like a function that has yield, if you remember from previous courses, that when we want to get some data, we can do it iteratively on that function. So for example, if you I can just give you an example. So if I have a function like, I call it generator, and I have some arguments into that, and I do some operation. I don't care what operation we are doing. And after that, we have a yield. We have a yield function here. And if, for example, we want to pass x from this operation. So this is kind of generator that we use for generating returning the x. And every time if I want to use the generator, I can, for example, say for x item in generator, and I do some other command or application on the x. So this is just an example that how generator works. If we have a list of x here, every time we just passing one item from that list, and in this for loop we are just looping through this x. So the data set here is working like the generator. So when we define data set, we are saying that, okay, we have a bunch of data, but I want to go one by one on each row of the data. So for understanding that better, I want to go inside the documentation of the generator. And I think I have it here. So I usually do not try to memorize things. And every time I try to go to the documentation and find the way how to implement these things, because during the time, the documentation can change. There are some other function can be added to the data set or other function that or other classes that we are using. So if you memorize, that's okay for sometimes, but after sometimes you again need to refer to the data set to find to documentation to find out what's going on there, and maybe there are some easier way to handling that classes. So it said that data set is an abstract class, and we need to define two main functions for it. One is the get item, and one is the length. And get item is exactly returning one row of the data set that we want. So for example, if you have a CSV file containing thousands of records, and we loaded in the initialization of the dataset class, and then in the get item, we need to return only one row of that dataset. And in the length, we return how many items we have in that dataset total. So if we define this type of dataset, we are able to create our data. This is an example I'm just showing you so we can modify it later. So suppose that we have a path for CSV file. It can be path for like images, anything else. But for this example, we have a CSV file, and we have the function loading from pandas for loading the CSV. So the first line here is just loading the CSV file, and it's going to the data frame. And suppose that the data that we have is like a table that each column are features, and the last column is the target. Maybe it's related to disorder that is a patient has a disorder or not, or maybe it's a binary, maybe it's non-binary output, maybe this is a regression problem. So the last column is the output that we want to predict. It can be anything, and other columns are just features. So we can do many things here, like the data normalization, converting data to, like here, as I've done here, like converting them to the float 32, changing the type and stuff like that. And After that, as I said, we need to define two functions. One is the lens and one is the get item. This is override on the abstract class of dataset. So I think you already passed the object-oriented programming. So by defining this class, every time if I say, if I create an instance of CSV dataset and if I loop over it, so I can get one example of data that we have. In get item, if we go inside, we see that we are saying return us the index from dataset for X, which are features, and index from the target, which are Y that we have. So let me give you another example. So suppose that we have a dataset of images. So I can define any name, like I can say image dataset or my custom image dataset, can be any name. And the only thing I need to do is just inherit this from dataset that we have in the Torch. And let me define this after, just to have not complain about the imports that we have here. This is just another example. So the only thing that I need to do is defining the initialization. Initialization doesn't need to even pass a path to it. And for example, here I can say my data set, and I can load it somehow. Maybe this is an image data set. So if it is an image data set, maybe I just want to load the paths of those image data sets. So maybe I can use some library like globe for finding all of the image in one folder. So for example, images are saved in my C directory and my images. So in this way, I have all of the images in the self dataset. I only need to do two different things: one get item and one lens. So I just copy and paste from there. So the lens function, as we explained, so it should have the length of the dataset. So I can just replace this with that part. And for get item, we need to return one of the rows from the dataset. So it can be like, for example, if you have dataset and I said this is like a path, I can comment here, path of the images in one folder. So in this example, so I can, for example, use CV2 OpenCV command for loading an image, and because I'm passing one index to it, so I can say from this data set, read the image index with IDX and save it in images. And maybe I'm loading the labels from somewhere else. Maybe I'm loading labels from the path that they have, or maybe I'm passing another helper here as a label because maybe I know the labels when I'm loading them. So they can be different scenario applied here. So in the return, maybe I can just I just want to return the image, not the labels. If I do something like this and I create an instance of my data set like this, so I can say this is my data set, I call it. So now my data set is created and I can loop through it. I have my generator. Every time I loop through it, I go to this folder, load one of the images, return the images. So this is how the data set works in Torch, and we need that for loading our custom data. Oh, there are some questions. I'm just wondering, should I go through it or we can leave it until we've done?
Yeah, we can cover Q&A at the end. May I ask you to increase your font size if possible?
Oh, yeah.
Perfect, thank you.
Do you know where is that needed?
I think you can probably just zoom your screen maybe a little bit.
Yeah.
Yeah, there you go.
That's perfect. Thank you.
So this is just an example I just want to give you that how we can write these functions that I've already written here based on our data. So we can define anything. Sorry. I just want to delete that. So the dataset is loading from Torch utils dataset because in Pytorch dataset, if you come here, it said Torch utils data. So if you don't know that how you import that, you can just search it in the Google. You don't need to memorize it, or if you're using some ID, just create the imports for you. So let's back to the quotes. So the next thing that we need to define is data loader. So when we define dataset, we are just defining the we are just creating a generator for returning each row of the data or each sample of the data. But for learning deep learning algorithm, we sometimes need to use like batches, or we need to put the data inside the GPU from CPU. So there are some functions that are being used for this kind of data creation. So there is a data loader in Torch. So if again go to the Google and, for example, we search data loader Torch. So we go to the documentation of Torch. Again, Torch utils.data if you want to import from that. And as in the documentation said, we need to pass a data set. So we already created our data sets. We can pass it. And we can say how many batch size we want. So if we want to use 8 sample in each batch, so we can define it here. And do we want to shuffle data or not? So we can pass that to the data loader classes. And we can have different sampler, like if you want to use random sampling from the data, or different kind of sampler we can use. So we can use different workers if you want to use multi-processing. So for example, if we are using 2 GPUs, and for each GPU we are using, for example, 2 batches. So we totally have 4 batches, and for each node of GPU that we have, maybe we need to define number of workers to 2. And in that case, we are loading data parallelly because the data loader go through the data set, load the data, and if we set number of workers to 2, it means that we can load data parallel together. And the collate function is sometimes we load the data and the data is not appropriate for the feeding into the model. So we need to change it somehow. For example, I just want to convert all of the images to grayscale. So I don't need to change the data set because maybe data set is designed generally and I don't want to change it. So I can define collate function for different purposes. For example, in computer vision in segmentation, maybe we want to convert our data from instant segmentation just to the object detection. So in the collate function, we can collate the input and output of the data that we are loading. Another thing is the pin memory. So if you're using the GPU, so we should set the pin memory true because it helps the data loader to copy the data from the CPU to GPU. And other function, if you don't know about them, if you forgot about them, you don't need to you don't need to memorize them. I didn't memorize them. I just use them and I just remember what I've used. So maybe in the future I want to need to use, for example, prefetch factor. I haven't used it so far, but maybe if you want to use it, so we can go to documentation and read and learn from it. So let's back to this. I have created a prepare data function that we pass that dataset path, and we create our CSV dataset. So the CSV dataset is defined in the bow. So we have our dataset. Now we need to use a data loader, and for data loader, we need to have a train and test data loader. That's why I have created get splits function inside the dataset, we can do it differently. For example, I can use the split function from the sklearn or scikit-learn or any other libraries. Just we need to split it somehow, and I use this function that we get the percentage of the test samples that we want, and just a simple split using random split, and this random split is defined in the torch. So it said give me the data set and define which indexes need to be trained, which indexes need to be tested. So I split that data set to 2 parts. You can use any other function here. I will show you some other example after we go through this to the end. So as I said, so we need to pass the data set. We can define the batch size here, and we say for training data, we want to shuffle. For test data, we don't want to shuffle. So now we have our data loader. That data loader can be a generator on the data set. So let's go to the creating our model. So for creating a model, again, we need to know.
Sorry for interrupting you. A few questions came up that I think at this point, if you address it, might be better. One question, first of all, feel free to send the question to everyone on the chat, but if you feel comfortable, it's okay to send it to me as well. What is the difference between dataset and data loader? That's the first question.
Yeah. So the dataset is just, as we define here, just returning one sample from the data. And we didn't have defined like it is running in GPU. It's not. We need maybe some feature transformation between the data and the place that we want to feed it to the model. So the data loader is a wrapper on the data set that handles some of the data creation and data preparation. In data set, we don't care about the batching and GPU memory, stuff like that. But in data loader, we just pass it and we say, we want to get data in batch. So each time I loop through this data loader, I'm getting 32 sample. And I can shuffle using data loader, and I can say pin memory to true. So it's copy all of the data to the GPU. But dataset doesn't have all of this. It just loads the data from the hard drive or the databases and stuff like that.
Oh, a couple of more questions that I go through them. Why we need a batch, and what is a batch?
Yeah. So where are those questions? I cannot see them. I can just see that how can we deal with multispectral data, 3 classes of images. Yeah. So about the batches, I can say that so for training a deep learning model, so it's sometimes we have some kind of normalization, batch normalization, stuff like that between layers, and this is like a sample from the whole of data. So if you want to use, if you want to find out the average of the data, sometimes it's better to have a larger batch size, but training on the larger batch size means that we are using much resources. The training rate is faster, but we need like a bigger GPU, because if you have images and if you want to load 32 images together, we need enough memory to load them together. So there are advantages of using batch even higher. In NLP, we have seen like even using 8,096 sample in one batches. That is, I think, the largest I've heard. And for image processing, we usually try to have at least 4 or 8 number in batches if we can. That depends on the image resolution. Maybe image resolution is not that much high, so we can use a higher batch size. So it reduces the time that we need to training, and also it will help for some layers like batch normalization and stuff like that to be fine-tuned better.
Thank you. Once again, feel free to share your question on the chat with everyone in the 2 session. You just 2 area, select everyone. If you are more comfortable, feel free to share it with one of the co-hosts as well. Thank you.
Yeah. We have created our data loader. So now we can load our data. But before that, we need to create our model. So for creating model, we in Pytorch, we use NN module. And the module is another part in the documentation. So if we go to the documentation, you see that we have torch NN module. And this is another class that we need to inherit our model from that. And there are some functions, but the more important function is the forward function. There are some other functions like backward function that we can define it based on if you want to use, if you want to define a customized network that back probe graph is different from the forward. But if our network is something very regular, like using the convolutional transformer, stuff like that, we don't need to care about the backward. We only need to implement the forward function. So what we do here is in initial function, we say what module we want to use. For example, in this example, there is a convolution layer and there is another convolution layer. And in forward layer, we say we get an input X and we pass it through the convolution layer and we pass it from the activation function ReLU. And again, we pass it from another layer. So layers is like convolution layer, activation layer, convolution layer, activation layer, and go to the output. There is no complexity in that. So if you want to define our model, the only thing that we need to know is what are modules defined in NN dot. So maybe we want to use convolutional one-dimensional. Maybe we want to use attention layer here. So we can define it here. And in the forward function, we just show the pass of the data from input to the output. So if we go back to the model that we have defined, so we are creating the MLP, a simple MLP for our cases, and I have imported torch NN linear, the ReLU function, the sigmoid function, and I will go through this after I explain that the NN module. So for creating the MLP that we have here, I first say that we have inputs. And these inputs should pass through the linear layer. And we call this, this is number of inputs. So for example, we have 5 inputs. This is a CSV data. For example, if you have 5 inputs, we say we have a linear layer that its input is 5, for example, and the output is 10. So it is like a dense layer that converting, or linear layer that converting these 5 input to a 10 output. The next things, I just say that suppose that we don't have this part yet. So I just want to make it a little simpler. So the next layer is defining just a ReLU. So I call it activation function 1. And because the previous layer is defined, output of that is defined 10. So the next layer should start with 10 because it's going to be after the first hidden layer. So we have second hidden layer. And in the second hidden layer, we have 10 inputs and 8 outputs. And we have another activation layer, activation 2. And as before, because we have 8 in the output, we again have 8 as input. And we want to just have 1 output at the end as the prediction that we want. Because the prediction, the data set I've defined is a regression. So we can have that regression, and I use a sigmoid function as the last activation layer because we want to just normalize the output to between 0 and 1. So this is the whole network that we designed, but the flow of data defined in forward function. So we pass the X as an input, and we pass it from hidden layer number 1, and we get it in the we pass X, we get X, and we pass it again from the activation layer 1. So this is called the layer 1, if you want to say what is the first layer of the network, the hidden representation and the activation. And second layers and the third layers, and that's it. So what about these functions that we have defined? So based on initialization for weights that we define, we can have different ways of initialization of random weights on the neurons. So if I create these like linear layers, I think the assumption is all weights and biases are 0. But if I want to have, or maybe normal distribution, I should check the documentation for that. But if you want to have a more academic way of doing that is using some random distribution, and we say to the system that if you want to initialize these weights, for example, the weight of the hidden layer number 1, I want to use some uniform distribution using k-mean uniform distribution random variable. So it will help the model to train better. In the training loop, I will comment these and run once with these initialization and once without it to see how it changed. So basically, some of the models are, this is very simple, but some of the models maybe are a little unstable, and you need to have a better initialization point, initialization weights to start training on them. And it will help to have a better convergence, and yeah, that's it. So we need to define the MLP module. So far, if we want to summarize, we have defined our data set, so we know how we want to load data. We have defined our data loader, so we know how we want to collate our data. We want to prepare our data and feed it into the GPU or CPU. And then we have our model, and we know that how model works. The next thing is defining the optimizer and loss. For training a network, what we want to do is we have the data, we pass it through the network, we get some output, and compare it with target somehow and create the loss and backpropagate that loss through the network to train the weights. So for this purpose, we need to define what kind of optimizer we want to use and what kind of loss we want to use. So the documentation optimizer and loss, let's go and see that. First, go to the optimizer. So when we want to train, we can do different optimization, like using the SGD, stochastic gradient descent, or we can use ADAM. So there are different ways, like the ADAM is using the momentum. I will go through them after the presentation. If you have time, I have some notes about the differences. And in the training procedure, I also change the SGD that I have with ADAM and ADAM weighted and show you how the performance can change based on the problem. So there is no superiority of any of the optimization. Some problem works better with the SGD, some better works with ADAM. There are some others like ADA delta, many optimization have defined. But based on the problem and based on the problem space, you should find a better approach. And usually if you search in your field, like if it is computer vision or segmentation, maybe some of these optimizer works better for you. So it's not, for some problem that is like new, you need to investigate more about them. But for some problem that usually we have a state of the art, so it's already known that which optimizer is better. So the optimizer is used for that if you wanna, if you have the gradient, if you have the loss, how we wanna backpropagate that loss through the network. So we have the previous weight plus the learning rate in the step size that we wanna, or the direction that we wanna go through for training a network. So this is for optimizer. And for loss, so we have the output that we want, and we suppose that this is the binary classification. So we can have cross entropy loss, binary cross entropy loss. Or maybe we can use KL divergence loss. There are different losses that we can define. So for example, we can say BCE torch. So you will see the documentation of binary cross entropy loss between the target and input, and see the formulation that how it works. So if we have the target and if we have the output of the network, there are some formulation that how cross entropy loss is defined. So again, this is also based on the instinct of the problem that we want to define different ways for that. So in this case, I've just used BCE loss based on the data. I think I will go through the data set and show you that how it is. The binary classification can works here, and we can use it as a regression also. We can train it as a regression, but use the BCE loss at the end. So here we have defined the train model function that get the data loader and get the model. We only need these two, and we have a main for loop for training the network. So this is the main for loop for passing the data through the network, getting the output of the model, getting the loss, back propagate through it, and that's it. So we define number of epochs. Here I define 100. You can change it to any numbers. And here, this is a part I talked about the generator that we have. So we have a loop over the data loader of the train data loader, and I use enumerate. So we have the index of the data, and also we have input and targets. So here in Torch, in Pytorch, we always should say that optimizer 0 grad, because when we are training a network and using the optimizer for training the network, each time we need to make the cache of optimizer free, because it will be saved into the optimizer. I will explain that a little more a few minutes later. So and let's go to this part. So we have inputs, and we pass the inputs to the model. So we don't need to say model.forward because we have defined forward. When we say model and we pass inputs, it's automatically call the forward function. So we pass the model input to the model and get the output. And now we have the output of the model, and we have also the target. So we need to compare this and calculate the loss somehow. And for this example, the loss is defined using BCE loss, but you can have different way of defining loss based on your problem. So now we have loss, and just remember from the previous courses that now we are creating the graph. So we have everything in the memory about what was the pass during passing this input to the output. Everything is saved about weights. So when we say loss backward, the Pytorch automatically know that what is the pass for going back when we want to train the model. So when we do the loss backward, it just initializing the weight or making the model ready for training. And when we say optimizer step, it uses the optimizer that we define here using the stochastic gradient descent for this case. And we go one step for training the network. So each weight inside the network is trained using back propagation, using this optimizer.step based on the SGD algorithm and based on the loss that we have defined as backward. So if I can annotate something here. So we have our MLP layers here and activation, and we have the last layers. So we have the output here. And when we say loss.backward, we calculate the loss and we put it here as loss.backward. And when we say a step, it go one step for all the layers that we have until end of the start of the network, and update all of the weights here. So I hope that it is clear. And there is a question I see. These are steps are supervised learning. At what step do we diverge for unsupervised learning? Does Torch also support unsupervised learning? So these are defining for the supervised learning based on the problem that we can define. Maybe we can use even the same things for unsupervised learning. For example, if you are using contrastive learning or you are using some sort of data augmentation, maybe you have two different ways of feeding a model, and you are just comparing the output of two models. I mean, I will give you an example if you have a time after the meeting. But just for a case, if you there's a paper called Bootstrap Your Latent. So this is an unsupervised method for learning, and in that method, you need to define your optimizer, you need to define your loss, but the input of the system is just one image that it's go to two different branches. One is augmented, one is not augmented, and the output is just comparing the augmented and not augmented to be similar or not. So again, you need to have a loss, you need to have the optimizer, but you are not using the target. You are using two different input, one augmented and one not augmented. So this can be an example of unsupervised learning that the main thing is the same. So you will see these kind of loop a lot when you see training of the deep neural network in Torch. One of the things that we need to care about is the parameters that we need to pass to the optimizer, like the learning rate, the momentum based on the method. If you are using, for example, SGD, or if you are using Atom, there are different things that we need to take care of them. I will talk about them. I have some notes at this notebook to show you how performance can change by changing this. So usually we like to have a smaller learning rate because it's better to find the the exact and the global optimum in our problem. But a smaller learning rate means that we are very slow in training, and maybe instead of 5-minute training, we need to put it in for 10 minutes. So yeah, thank you for that paper. If we have a time after the meeting, we can just go to some of them. So another part that we need to define is the prediction part. Now we train the model, and we need to go to the prediction part. Let's run the code until this part and see what's going on so far. So we have this part. Nothing will be run because this is just definition of the classes. But let's prepare them, because if you want to train the model. So let's go to the next part. So we have the prediction. The prediction get a row and row of data and model, and we just need to convert that row. Maybe this is a NumPy. We need to convert it to the tensor. There are different ways, like using Torch as tensor or using this tensor. There's not unique way to doing that, but we convert it to the Torch tensor, and we pass it through the model, and we get the output. And the output can be inside GPU, because if we use GPU, our model is working in GPU, and the output is in GPU. So there is a function detach, and also, as I said, the model is on the graph. So the detach means we don't care about the rows that the data pass. We want to detach it from the graph. We just want to get the value out of it. Because if you don't detach it, again, I can say backward. I can use this command, and I can train it based on this y-hat. And there are lots of memories consuming here, because we are saving, if the model is big, we are saving lots of information about the routing and graph inside the network. But when we use detach, we are just detaching this value from the whole network. So it would be much simpler and also lightweight. So we get the output from the model. So this is the prediction loop. This is very easy. Just need to convert the data to Torch, pass it to the model, and that's it. And in the next part, which is important, and the title of this conversation is training and evaluation. So we passed the training, but we need to evaluate model. So we create a test dataset, data loader, as you remember, and we have the model. So we need to have some metrics like accuracy or F1 score or recall, anything else. But for simplicity, I just put accuracy here. We can define any other metrics here. If you have time, I will go through it definitely. And what we want to do is we get a list of prediction and the actuals, and we loop through the test data loader. It is very similar to the training loops that we have. And we loop through this data loader, we get the input and target and pass the input to the model and get the output. And because we don't want to train, we can detach it and make it lightweight. And we have the y hat as the prediction of the model, and we convert it to the NumPy. And also, this is important to know that the Torch has some functions that you can easily use for converting data to NumPy. Instead of this, you can you can say NP as array, and that's the same things. But for output of the model and the actual, we convert both of them to the NumPy. And because the actual is just maybe one label, we need to change that to be same as dimension of the prediction. So we just reshape it. I will show you after I show the data that how the output is. Output is just a number like 1 or 2, and the output of the network is the y hat is based on the output of the network is like a vector. It is always one dimension, but it is like 1 by 1 vector. So we need to just change that to the size of the output of the network. And we also round it because, as I said, we are training the network based on the regression, and everything is between 0 and 1. And finally, we round the output. So everything is now just 0 and 1. And we have prediction appended to the list and the actual appended to the list. And the final thing is that we vertically stack them together to have the same dimension, and using the accuracy score for finding out what is the accuracy here. So the accuracy score is importing from scalar. You can use F1 score. You can use other metrics here. And the actual is what we have in the target. It is like 0 and 1 labels, and prediction is what we got from the model. So we get the accuracy that how much accurate our model is. So now we can go to the main pipeline, and I can explain the data, and we can train the model. So the data I have defined here is based on the UCI machine learning, a liver disorder dataset. Let me open that. And the dataset is mainly related to effect of alcoholic beverage on the liver. Let's see the names of the variable here. So as it's explained here, we have blood test from 345 different people. And the 5 first features are features that are extracted from the blood test. And it's showing that a person is using alcoholic beverage, the number 6 feature, how much its drinks affect on the liver disease. And the number 8 is missing value. Let me open the data also. Maybe that would be better. So this is the data, as I said. So we have 5 first features coming from the blood test, and the next one 1, 2, 3, 4, 5. Yeah. The next one is defining the person is how much alcoholic beverage is using. And the last one is the classes. So classes 1 and 2, and I think the 1 means that the person doesn't have a liver disorder, and 2 means that the person has liver disorder. So this is the whole data, and as we define the prepare pass, we can just pass this data to get the train data loader and test data loader. And we create our network using 6 input, because we already have 6 input here from 1 to 6. So we have these 6 input, and that's why I select 6 as a number of inputs for the MLP layer. And we have our model, and we say train the model. So we have data loader and also model, and we can train the model. So this model, after this slide, will be a train model. And then we evaluate it using the test data loader that we have. And we get the accuracy out of it, as we explained before. And this is just another example to see if you want to use the predict function. We define maybe another case COM, and you want to find out that this person has liver disorder or not. So if I run this, so I'm getting about 49% accuracy. And for this case, it predicts class 1. So first of all, let's have a case. I don't know that this is coming from test set or train set, but just for an example, I know that this person is 1, so the class label should be 1. So just giving you an example that how we can feed data to the model. And this is 0. So you know, the accuracy is not. We expect first of all, we expect that this would be class 1, and in this loop, we want to improve this accuracy using what we have learned so far. So let's go back and see how we can improve these things. So the first thing is I have some features, as you can see here, that features are not normalized. Like I have 88, I have 8. So for training a network, it's better to normalize feature. And for normalizing, I can do it in the data set, or maybe in the collate function of data loader. That can be happening both. So I have a comment here. So one of the things I do is I'm just using the Z-score normalization. So it means I get the data, I get the average of each column, I subtract the average of each column to the data and divide it by the standard deviation of each column. So it would be a Z-score normalization, and data now is normalized, should be normalized to the Gaussian distribution. So if I do this and I run the data set again, come back, create the data loader, I have to do this for all of the pipeline I have, because I changed something from the inside of the model. So I have to run it from scratch. And now I can come here and train the model again and see how it is. Oh, and you see from 49, now we are getting a much higher accuracy, about 69%. And the reason is that the data now is normalized and can be handled by the model better, especially the weights that we defined here are initialized using some of the, random weights that usually are between 0 and -1 and 1. So if I comment this, just want to show you that how these can affect on the system. So I have to run the whole pipeline again. Okay, so you know, the initialization is very important to the network. Of course, there is a randomness inside the loop, because when we shuffle it, every time I run it, it's not persistent. So it's maybe creating the terrain set and test set from different part of the data. So it's not meaning that it's getting better or worse, but we can say that at least when we have a drastic change, and if you run it like 5 times, 6 times and get average, so we can have a understanding that this change was effective or not. So let me do that. So if I come here, so I don't have those initialization dates. So I run it again. Okay, so it's getting from different part of the data. It's getting the terrain and test set. But if I, for example, run it for 5 times and get average and the standard deviation, that would be like holdout approach. So I just want to show you that it is always more than like, so far it is always more than 60%. But if I, again, back here and remove the normalization part, and I run it 5 times again, okay, cool. But you see the average is really lower than the previous one. So it means that if we write these as a documentation somewhere, we will see some sort of improvement coming from the normalization. Another thing that we can do is, let's back to the one of the things I forgot is this a uniform distribution that we have. I've just defined it here because especially in some unsupervised learning, these are very important that if we don't define them, the network cannot even train. For this case, this is very simple. This is not effective as we think, but in some of the network, like for example, in Siamese neural network, if you don't define this kind of initialization for weights, your model cannot be trained at all. And magically, if you put some sort of initialization, you will see the convergence. So another thing that we can do is changing the learning rate. So if I make the learning rate bigger, let's see what will happen. So let's back and be sure that the normalization is on. We are getting more than, I can say maybe more than 70% accuracy for normalization on back. And if we have a learning rate to 0.1, so I increase the learning rate 10 times, let's see what will happen. So also it is good to see the trajectory of the loss that when we train it. So I will try to have some example from that too. So you see that the learning rate in that case does not make any problem for the stability, but in some networks, if we increase the learning rate, the model cannot even learn because it go through some ping pong situation that the points that you want to optimize is going back and forwards between 2 different local optimum, and the network can't be trained. But for this case, if I make it very small, and let's have it. So yeah, you see that the network, based on the number of epochs that we have, cannot be reached to the point that we previously have using the higher learning rate. It doesn't mean that the lower learning rate is bad. Usually we prefer lower learning rate because it is much stable and giving us better results, especially in bigger networks. But one of the things we can do for this case is increasing the epochs. So if I increase the number of epochs instead of 100 to 1,000, so now I have a smaller learning rate. So the network is more meticulous when it's searching through the problem space, but we give it enough time, like 1,000 steps instead of 100 steps. So let's go back and run this. So it will take a little longer than before, but we expect to reach the previous accuracy or even better. No, it needs even higher. Oh, and the learning rate is backed. Yeah, the epochs need to be higher. Let's come here. Maybe learning rate is too low that for this problem it cannot be trained anything, but let's see how it is. So usually these kind of fine-tuning the models and the training pipeline is important because sometimes just changing the learning rate drastically change the outcome. For example, I can give you an example for language model in NLP that there is a number for learning rate 2 e minus 5, which is very famous in training language models. And if you change it in some of the models, for example, in BERT and Roberta, you will not get that accuracy that is reported in the papers. So these learning rates and also number of epochs, the normalization, data engineering, feature engineering are very important when we want to train. It is still training. You see that it's taking longer. I hope we can get at least same accuracy as before. If not, it means that this learning rate is not good at all for training this kind of data. So while it's training, I'll go to some of the other things that we can do. So we can change the loss from BCE loss, binary cross entropy loss, to some other loss. So cool. We have the results. So accuracy 73%. So we see that increasing the epochs and decreasing learning rate, we could get similar accuracy, but takes much time. And also you see the predicted class, because I converted all of the class from 1 to 2 to 0 to 1. So 1 should be 0, and it means it's predicted correctly. So let's back to the loss that we have defined. So another thing that we use is the KL divergence loss instead of the binary cross entropy loss that we have defined. I have prepared a note here, but what is the difference between these two? If I found a good answer here. So this is the definition of KL divergence, that it has the binary cross entropy, but it has also the entropy of the target. And it means that the both things are trying to create a divergence between the two probability of the the two classes inside the system. So if you have two, for example, for this data set, we have two different groups, one with liver disorder, one without liver disorder. So what we want to do is to create more difference or distinguishable line between these two probabilities, between the people with disorder and without disorder. And in KL divergence, what we want to do is we get the binary cross entropy between the target and label, and we need to know the entropy of the target. But when we train the model, we do not have the entropy of the target. We only have the entropy of a small sample of target, depending on batch size. So this is another part that batch is important, because if we increase the batch size, this HP, the entropy of the target, is more closer to the reality. But if the batch size is small, it's the entropy of just that sample that we are training on. And that's why the binary cross entropy in most of the time is more stable than the KL divergence. But for some cases, we can use KL divergence and we can get a better accuracy. For example, in GAN, many people are using KL divergence loss for their image-to-image generation or stuff like that. So one of the things that we can do, as I said, maybe we can change this BC loss, and maybe I don't know what is the KL divergence loss in the Tor, so I can easily search that KL divergence loss. So there is a KL div loss, and there is a formulation here. What I can do, I can come here. There are some example, and you see that most of the time we are passing like softmax, because like this is the problem of classification, but we just need to this part. that we need to change our loss to the KL divergence loss. So I can do something like this, and instead of using NN module, I can import it from here. So I just changed the loss to KL divergence loss to see how it is. Yeah, and also it said there is a warning here that mean divides the total by both batch size and support size. So there are, as I said, the second terms is related to the how we want to estimate the entropy of the target, and that depends of the batch size that we are passing to the system. So there are some function related to using the reduction of mean. We don't care about the warnings for now, but it's coming from that point that the KL divergence is using the entropy of the target. So let's back the learning rate to something that we had before to not take time, and the number of epochs to something smaller, maybe 1,000 or 100. I want to stop that and using this learning rate and to not take time. Okay, so I just want to give you an example that another thing that we can change is changing the loss function. So you see that the accuracy is 62. So seems that the BC maybe is better. It's not deterministic. We should run it for 5 times, get this standard deviation and average. This is very important when we want to report something, especially in a medical domain. So we should have confidence intervals. We should have average that we report and standard deviation, all of that. So another thing that we define is the weighted loss, or using some regularization. Instead of SGD, maybe we can use ADAM. And if we are if you want to find out what is the difference between ADAM and ADAM weighted and SGD, there are some good papers. I can give you one of them here. I found it very helpful. It's defining different optimizer from RMS prop to ADAM and stuff like that, and explain why they have defined and how they works and what is the difference. I don't want to go out of the scope of this class, but it's very important to know that based on the problem, which one is fit for your case. And so, for example, I can use ADAM here instead of SGD, and simply I can come here and replace it with some ADAM. So, for example, I don't know how to use ADAM. Again, I come to the documentation, I search ADAM torch, and in down it will give me some example, or if there is no example, I can use the ADAM from here and use the parameter it's mentioned. So I can come here and say I want to use ADAM, and I want to use ADAM on these model parameters. This would be same, and learning rate would be same, and this would be my optimizer. I just need to import ADAM from this part, and I also want to return it back to the BCO loss to have a consistent report. So we have ADAM. What other things that we what other thing need to be defined is everything is predefined. When we see like this one, even if we don't define learning rate, it is already predefined like this. So I'm just changing the learning rate to 0.1, 0.01, and so we have optimizer ADAM now. So we can again come here and train the model. And see how it is. It's finished. While it's finished, I can say, okay, again, same thing. So this is not a very hard problem. So that's why and maybe changing these is not effective enough to see the changes. But these are very important parameters that we can change during training. Another thing is using the weight decay. So instead of it is like L2 regularization that we can use during the training, the weight can be attenuated, and that can be also helpful. So this is the point that we can use for training. I have also another, I can send these links in the chat. Maybe you are interested to see how they are. I found these very helpful for finding the optimizer, the difference between the divergence that we have, the loss that we have, and yeah. So another thing that I want to discuss is, instead of accuracy for evaluation, maybe we need to use some better metrics, and that depends on the data, that how many data that we have, the balance of the data. Maybe we are using an imbalance that it is very usual in medical domain. And for these kind of purposes, we need to use other metrics. So basically, I don't know that it is covered or not, but if we have the table for classification confusion matrix system, we need to know the true positive, the false positive, the false negative, and true negative. That I hope you already know. And the other parameters that we can define is the sensitivity, the specificity, the precision, accuracy, and AUC and F1 score and MCC. These are very important parameters that when we want to report something, it's good to have all of those. So let's back to the code. I'm using the scalar metrics. So suppose that we don't know how we want to use other metrics, how we want to bring, for example, F1 score to the system. It is very simple if we search for scalar metrics. So we will come to the metrics that defined here. So we have the F1 score, AUC, the other metrics that I showed you in the book there. So basically we can, for example, we can use F1 score as we used accuracy score here. So if I come here and replace it with F1 score, so now I have access to the F1 score, and when I am calculating the accuracy, maybe I can add the F1 score. So I can say calculate the F1 score here and call it F1. So here, instead of only returning accuracy, I can also return F1 score, and I see the report more comprehensive. So here, when I evaluate model, I need to add F1, and also in the print function, and I can use F1 score. So now we should be able to see the F1 score too. So let's run it another time just to see the F1 score. So the F1 score is the weighted average of the recall and precision. And if you have imbalanced data, it's really recommended to see the F1 score and also the AUC. And AUC is the average of the sensitivity and specificity. And let's add the AUC to have a better conclusion. So this is very simple for adding the AUC. So we have ROC AUC, so we can say ROC AUC. I'm just using documentation. I don't memorize, and you don't need to memorize too. Not here. It should be here. So when we calculate the F1 score, we can also do the ROC AUC, and we say actual and prediction coming here, and we say this is AUC and return the AUC. So it would be like adding different parameters. So it's better to have like a dictionary or stuff like that to add only one metrics, And when we want to report, we don't need to add again this kind of print each time that we want to add any metrics to the system. And so there is another function. That's why I think this is report accuracy, something like that. Yeah, classification report. So if you go to the classification report, there are some example. It can return us the precision, the recall, and F1 score, not more than that. But if you want to get some sense of how the system is working for different classes and for micro and macro average and weighted average, so we can use classification report from same path that we use the accuracy score, F1 score, stuff like that. And I think there are some other functions in the Python that we can return a comprehensive score from the system. So there's a question, say, when the classes are balanced, the best criteria for evaluating the classifier is accuracy. Is it true? The F1 score is better when we have skewed classes. So yeah, that's right. But the F1 score is also skewed to one of the classes. I mean, let me give you a sense here. I encourage you to see this chapter book that we have written about different metrics that we have and when we use which one, and about imbalance of that question, because this is very important to know that if we have imbalance and in which circumstance we should use which one. So yeah, so if for example, if I'm trying to say it right, because finding out between TP and FP is sometimes hard, but if we have F1 score and we have data that most of them are with disorder and many few of them doesn't have disorder, F1 score would be high, because in that case recall is high if you are predicting most of the people as with disorder. So the F1 score should have condition for imbalanced data that most of the data that we have is not with disease. And if in the inverse condition that most of the data that we have is with disorder condition, F1 score is also biased. And in those cases, AUC and MCC is better. I just want to pinpoint to this point here that we are saying here that the accuracy and F1 score also has the classification problem. And among the composite indices, AUC and kappa could also provide repeated p-value measures supporting the statistical interpretation. So at the conclusion, the AUC and the kappa and also the MCC are the more stable indices for reporting the performance accuracy. But anyway, having a confidence interval and also the standard deviation and average of the run, like if you are using holdout, average of the run like for 5, 10 is very important. If you're using k-fold, also reporting the each fold accuracy and also the average and standard deviation is very important too. So let's back here. So as I said, we want to add AUC. So here we added AUC, we just need to change it to pass another parameter. So AUC is the average of the sensitivity and specificity. So it would be more stable against imbalanced data. Oh, I didn't add the print. Let me add the print. Yeah, so in object-oriented programming, I think you have passed this tutorial that instead of using these, it's better to have like a dictionary here, and we define it and pass that as a metrics and just show the metrics here instead of just repeating some lines of the code. So yeah, so we have the F1 score, the AUC, and the accuracy. And we can add any other things as we want. So I'm open to any question that if you have. I hope that I covered most of the things that I need.
Thank you so much. So do we have any questions from the audience? Farhad, did you get any more questions from the audience?
No, I think I haven't received any question. Feel free to share your question right now. I think one thing that this is perhaps based on your experience, Mohammad Reza, I want to know what is the most important main area that usually people who start working in developing machine learning models, they make mistake in this means during the whole process from data digestion all the way to evaluation based on your experience and interaction with the students?
Oh, yeah. And thank you for a question. That's a very good question. So basically what we do usually is for each step that we take, we always like to see a log or visual output, especially for like computer vision that we do segmentation. So we need to see, for example, after loading the data, is it loading correctly? So it's good to save them as some example. So we can write some function here like sampling, and we just save some sample to see if data is loaded correctly. This is the first step. And the second step is usually defining the initialization variable here. For this problem, maybe this is not important, but for many problem, it's drastically changed the outcome. So that depends on the initialization. The learning rate can change, the convergence rate can change. Another thing that is important is checking the learning rates. Sometimes we train the model and we feel that the model, maybe architecture is not right, the model cannot train, but the first thing that we need to check is what is the learning rate that other people are using as a state of the art, and we use the same. And if we don't get the good answer, then we can go to change the architecture and other parameters. And also another thing that I will try to cover it in the next session is to tracking the loss trajectory. So here, when we train the model, I just create the function for training model, but this loss can be saved somewhere. Like we can say loss.item, and we save it as a trajectory loss. So this is covering the question that how to check if there is overfitting too. So we can say trajectory loss that append, and we have a list of trajectory loss here. And when we train the model, we also, maybe this is a global variable, or maybe this is returned from this training loop. So we can get all of the loss during training, and we need to have a validation set also, and check the validation loss convergence and training loss convergence, and see if the training loss convergence is getting lower and lower. Is validation convergence loss is following that, or it is not? So because maybe the architecture is not stable, maybe initialization is not stable, we need to check the trajectory loss for training and validation and compare them. This is very important to see the model is training or not. One of the other things we can do, if we don't have validation, maybe data is not enough, we can use our test set, not for validation, but for checking that the model is not overfit. So if we use like k-fold cross-validation and we train it, and we have the accuracy for train, here when we calculate the accuracy, instead of passing the test DL, we also pass the train DL and compare the accuracy and F1 score of test and train set data loader. So we can also check that if there is overfitting happen or not. So this is another important thing that we need to care. And all of the things is like neural architecture search or fine tuning that you can maybe automate it using some optimization, like a particle storm optimization, a stochastic optimization, or any other kind of optimization maybe can be used for what we have done so far. So there are some libraries that you can use, and those libraries just changing these, or maybe grid search on the things that we already changed and find the best way for creating the model. So you don't need to put time to find out which one is better. Yeah, that's it.
Yeah, and we actually have a similar question just now that you already mentioned how to plot the loss function. One question that was sent to me was how to plot the learning curve with respect to epoch number.
Sorry, can you ask again?
How to plot the learning curve with respect to epoch number.
Oh, yeah. So here, as I define here, so we have a trajectory loss. So for each data that we are loading here, so we are saving the loss. So we can, this is the trajectory loss for each data. So we can have an average of that loss for each epoch. So I can say this is, I can define it here. It's better to define it maybe here. And for each epoch, I can say training trajectory epochs here. And when I go out of one of the for loop, I can just say trajectory epochs append and get the average of like using NP mean or maybe torch.average, get the average of the trajectory loss that we already saved. And in the next for loop, it will be again empty, save the trajectory loss for the whole data for this epoch. And so if I want to complete it, so it would be something like this. And now we have for each epoch, we have the loss, average of the loss of the data for that. Maybe we care about median of the loss or anything else, so we can use that.
Yep, great. And did we talk about the cross-validation technique? You mentioned k-fold validation just now, but there are other types that may be specific to different the specific data sets. I think it might be good to showcase that.
Yeah, sure.
Especially for imbalanced data and different techniques that we can use.
Yes, sure. So that depends on the as Yajing, if I spell your name correctly, if based on the data, we have to define the data separation, data preparation for train, test, and validation. So I used, for our case, I just use a random split because I have enough data. But if you don't have enough data, there are some ways like bootstrapping and that you can use. So you have to write some function. I'm not aware of, is there any bootstrapping inside the Torch or not? But yeah, seems there are. I haven't aware of. But for example, if you want to implement it from scratch, so for example, you have 50 different samples, and you want to use bootstrapping, so you have to, for example, get one of the sample from the model, train on all of the sample, test it on that one example, and repeat it like 1,000 times with different substitution, with different permutation. And there are some kind of other bootstrapping method use different algorithms, but you have to implement it here. So we can have the original structure, like having the data set, everything, but just when we want to define the train and test data set, we go through that loop for bootstrapping or using the fold cross-validation or the random split that we have here. So I usually use the sklearn for separating the data, but for this time, because I want to use just Torch, I just use the random split. But if you want to use, for example, if you want to use sklearn, you can use on top of the Torch library that we have. So I can. Okay, so this is, for example, an example when we want to use Bootstrap. So we can create a cross-validation using Bootstrap, and when we have when we can get the training index and test index for different iteration, and we just use the random split that we have and pass the indexes to there. So this is just a simple modification that we can do only on the on this get split and have different variation of the splits that we want. So I'm just saying that we should not be only focusing on just one library. Maybe you will find other library for your use case, for your data split, or maybe data preparation, normalization. You can use any kind of combination of the libraries together.
Yep. And previously we had a we had a question about an example using Pytorch in unsupervised learning, and said if we have time in the end, we might be able to demonstrate that.
Oh, yeah.
And maybe you want to share this notebook, this updated version later on as well, because some stuff has been it's a little different from the initial version that we uploaded because we try new things.
Oh yeah, sure.
Yeah, so thanks.
So about the unsupervised, I'm just giving you an example that how we can use the same thing. So this is the main loop I've mentioned. So we have a teacher network and a student network. And usually these networks are using the same weights. It's called different layers like view, representation, projection, but you can suppose whole things as like a MLP layers, for example. So we have our images and we don't have any target. That's why it's called unsupervised learning. So for example, we want to separate dogs and cats without having any label. And the images that we have here is first with augmentation, and those augmentations sometimes is intensive that change the image drastically. And what we want to do in this kind of unsupervised learning is if we feed the augmented data to the network, same network, and if we pass the images without augmentation to the same network, we should be able to get the similar output, because we want to model to understand that these data, even if it is augmented, it is representing the same things that we want. So this is kind of unsupervised learning. So basically what we need to do here is just define, for example, those MLP layers that we have, but maybe the output is like 256 or any other number of tokens that we have. And at the end, when we want to calculate the loss, it's, for example, it's just getting the Euclidean distance of these two output from the two head of the network. So again, we have the same training loop that we have. So for example, if I come here, so again, we have, for example, inputs, and the inputs with augmentation, we do it inside the data set. So for each image, we can implement here like a function, data augmentation. And when we want to return something here, we can return data without augmentation, data with augmentation. We don't have any label. And in the model, when we get the output, we define loss. For example, based on the paper, maybe we use the bio loss, but here maybe we can just use the Euclidean distance, and we say the output of the network for image with augmentation should be same as the output of the network without augmentation. And all of the other parts is exactly same as what we have. So this is as an example of bio. Other example is like Siamese network is exactly same as this. So we have two head of network. Every steps are same, but in unsupervised learning, there are some small points that when you want to train, it's usually unstable. So those random initialization, learning rate selection, and also checking data, like seeing the augmented data or comparing with the original data is very important, because this is very unstable in some of the algorithm. Even for the bio, they mentioned instability.
Thank you very much. And just on the notes of validation methods. So last year, it was actually Farhad that gave this validation lecture as well. And personally, I really enjoyed reading one of his papers that I thought was very pedagogical. So I'm gonna just share in the chat. It's called Machine Learning Algorithm Validation from Essentials to Advanced Applications. So feel free to read them as well. And every time I feel like I need a refresh on the knowledge on what method to use for validation, evaluation methods, I would go to that paper. So Is there anything else you guys would like to add? So I just send the paper in the chat as well.
Thanks for sharing the paper. On that note, we have one session that will cover different approaches for data evaluation, data splitting, as well as how to evaluate machine learning models, and some pitfalls, errors that commonly people make, and they might affect generalizability of those models. So we have one session on that, and also we have one session that covers concepts such as unsupervised learning. So
Yes.
that's, you will see that down the road.
Perfect.
So I think we have a little bit of time, since one main challenge that I have seen some students faced with when developing machine learning model is that they try to build a model and train it for 100 epoch, and after 100 epoch they check if they have a if the model is working, if there is a bug somewhere. And sometimes this means that they spend a period of time on really training models that by default those models are buggy, they are not training, nothing will update. So those are things that you should be aware of when you train your model. The best thing is that, as Mohammed suggested, try to check different components of the model before training the whole pipeline. When you train the whole pipeline, it's completely acceptable in the training mode to make sure that the model is training to overfit the model. That might be seen counterintuitive, but you first overfit the model. How to do it? Most often the best approach is to use a small portion of the data, overfit the model, and then when you see the model overfit, means that model can memorize and learn. Memorization and learning is not good. We do not want this, but it's a clue that model is capable of learning. This means that your model architecture is correct. The way that you train the model, training loop is correct. When you have that, at that point, you can decrease the size of the data. So the best way to decrease or increase the most easy way actually way is to, in the len function, instead of returning the len of the whole data set, return a fraction of it. This means that at the end, you just need to change one line of your code to have access to the whole data set. That's one thing I suggest. Being able to see if your model is overfitting and underfitting is important. Mohammed suggested that how to find out if model is overfitting. Usually that one is if you have a correct test set, you can easily see that. We'll see down the road how to really pick the best representative test set for evaluating your model. For underfitting, of course, it's not that easy sometimes if the model is underfitting or not. For that case, sometimes you need to gain more information, talk to experts. For example, if you are developing something for a radiology application, you can ask doctors, what's the percentage of time that you can predict correctly based on your experience? And that one might give you a good performance. If they say in 80% of the time, I am able to predict based on just by looking at this image, that means that your model should do, if you want to reach that level, should do that around 80%. If your model gives you 70%, means that there's a gap. You need to improve the performance of the model. That's also something it's a good idea to consider. Mohammed, do you have any other hints or suggestion to add?
No, thank you so much. That was really helpful.
Okay, perfect.
Great. And do we have any other question? If not, this will conclude today's session, and the next one would be this coming Wednesday, also with Mamad as well. I think it's implementing your first image classifier, I think. Yeah, great. Thank you so much, and we'll see you later.
Thank you.
Thank
Bye.
you.